you are the right place. It should not happen that you are analyzing a bridge of Jhansi and by wrongly putting latitude or longitude, you are working in Florida or somewhere. So to keep on getting that idea, it's always a good practice to keep this OSM map in the background. And whatever regarding most of these things regarding GIS, what I'm telling you is there are, as I told you, there are a lot of communities. One of the group which is which works very beautifully on this use of GIS for hydrological application is TU Delft, Technical University Delft in Netherlands. They have published a lot of monogram. In fact, there one gentleman is there. Just let me see. I forget the names.
Hansen Craft.
It's Hans Wonderquast. He has got a YouTube channel also. If anybody wants, Hans Wonderquast. He is a senior lecturer at TU Delft. So they have published a book also, Hans Wonderquast and Kurt Menke of US, which we have got also. So I have in fact followed the same terminology. I have followed most of the things same from there for the sake of uniformity, so that if you raise any query and all to them also you can get an answer. So the basic methodology, maybe you can see 60–70% of this is what they have developed, and then we have made some changes to suit for our conditions. So this is how now you can see there are two rectangles here. This is one DEM, this is another DEM which is loaded, and background is your OSM map. You can as well load the Google map also if you feel comfortable. But my experience is Google map is too dark and too intrusive and takes more computational power also. Now next is you combine these two DMs because we have to work as one DM, and again they use a term mosaic. It is basically combining, merging the two DMs. So merge these two DMs and we have saved that layer as DM mosaic. So you can see here. Now other two layers we have removed, and what is layer which is being used DM mosaic. And those layers are available in your file. As I told you, you make a common folder, so whenever you want you can recall. Only thing is you are not cluttering it here and here. Here you are displaying only this. And this also, whatever layer you want to display, you click, otherwise you can unclick it. You can remove this also. So now you can see that whatever was the boundary here between the two DM tiles, it is also called as tiles, that has been removed and it has been merged into a single entity. So this is second operation. Next thing what you do is reproject the DMs. Now what happens is, see, this is what these DMs, they are essentially satellite pictures and you are seeing them in 2D. So it depends at what level, at what projection level you are seeing them. So whatever level these photos are taken by satellites and what level you are seeing and analyzing them should be common. Otherwise there will be parallax error. So in Bhuvan, and most of this you can check also. Here I will just show you, or next slide I will show you. You can see that your DMs are, that level or that plane is known as EPSG code. EPSG is European Petroleum Survey Group, again a standard platform. So in EPSG, this is the plane 4326. Whatever photos you have taken or satellite images you have taken, they are in 4326, which is actually UTM zone 46N in WGS 84 system. So if you want to know the EPSG code of satellite pictures which you are using, you can either go to this website www spatial reference. There you put your EPSG code and it will tell you. So you put your picture and go to properties. You can find out in which EPSG code it is there. So we have to bring them to a common projection platform, and for this whatever zone 46N, either you write EPSG 4326 or another way is you write them as EPSG 3246. For India, rather than going to this website, the best way is these three letters will always be common, 326. Only this two letter will change and that will be your UTM zone. So since these Bhuvan photos are taken from UTM zone 46, that's why it will be 46. If your zone, UTM zone, in this case, like it was 44. So for ours, this EPSG code will be 32644. Simple to remember. It can save some time. So then what we will do is these we will reproject to our EPSG code. As I told you, for us, EPSG code is 32644. So you reproject them to this, and I will show you here. Now there is a command and all which we'll do, and this is reprojected. Now this is reprojected DM, and here also this is known as on the fly projection code. Here previous things, if you see, like previous one, it was coming 4326 here. That is the default EPSG code for Bhuvan satellite pictures. So this we change it to ours, 32644, and this mosaic DM also we have reprojected, and we have given the name as DM reproject. Now if you see carefully, actually what was a perfect rectangle, it gets little bit distorted. Sometimes it becomes like this as edges become. That is because of reprojection effect. So this is next thing which we do. We reproject them, bring the projections in the same. Then subset or clip the DMs. Now we know out of this full mosaic DM, our catchment will be some part of it. Here there is a sort of catch. If you take very big area, then your processing time will increase, your processing power required will be more. Whereas if you try to cut it too short, maybe your whatever was relevant catchment area, that itself may cut. So taking care of this too, you will clip the DM. I will tell you how we will do, and save the layer as DM subset. So what I do normally is, if there is a rectangle like this, you try to fit best maximum size rectangle in this. You can change the size of this and leave it there. Don't try to cut it too much, otherwise in this process you may end up trimming some useful area also. So this is good enough, and whatever size goes here, there and all, that much extra margin we have taken while selecting the DMs. So there are commands for that. Using that, now you have arrived at DM subset or clipped DM. So now again it is looking like a perfect rectangle, like what it was looking before reprojection. So this is the DM. They are all part of processing the DM. Now there is another step which is called fill sinks or remove spikes. See what happens, many of you must be knowing, when your DM process is processed for making the flow direction, how it is done. Every part of your DM is divided into small cells, and every cell has got a value. Let us say that value basically is related to its elevation. So let us say this cell has got value 56. Now flow from this cell will go to the cell which is at the lowest flow. Let us say this cell has got value 58, this cell has got value 59, this has got 54. Then flow from here will come to here. Like that for every cell. For this cell, where flow will go, the software will check all around this cell. Whatever is the lower cell, whatever is the difference is one, it will go in that direction. So this is how flow is generated. Now in this, let us say we take this in physical shape. Due to processing of these DM from satellite picture, or maybe at the part of capturing the data, if there is some local sink, what we call means local depression or local spike like this. Now what will happen is, when we go to that cell, let us say this cell is here. Now this will be the lowest point and all around will be higher. Now flow will not go from here. It will, you will get, your software will get stuck up here. These are sort of artificial, features on this, which will create problem in your processing. So we have to remove what this is known as sink, similarly spike. They are artificial things which have come into your satellite picture because of processing error or some other error. So then there are various logarithm, it calculates average slope, and then something which is suddenly out of this or more than, less than this, it removes it, then again checks it. There are various type of logarithms, but that is what is called removing sinks and spikes. So this is like addressing up your DM, fill sinks or remove spikes. So there are tools in this, fill sinks and remove spikes. As I told you, there are various algorithms. One of the algorithm, which again people by experience have found works very well for this purpose, QGIS for hydrology, is an algorithm developed by Wang and Liu in 2006, and this is available in QGIS. This is available as one of the processing tools. So using this tool, you will fill the sinks and you will remove the spikes, and then this we have named as DM field. So now your DM will look, now even though visually it may look like exactly same what was your DM subset, but there is subtle differences inside, and now this DM field layer has come here. So you have done this operation also. After that, next step is,
excuse me sir,
yeah, yes,
सर जी हम सेल्स ले रहे हैं, इसका अप्रोक्सीमेटली सर ऑन फील्ड साइज कितना रहता होगा एक सेल का सर?
That depends on what is the resolution. Actually, what photos for Cartosat 3M, which is available free now, 1 DM, its accuracy is 1 arc second, and 1 arc second roughly comes out about 30 meter.
सर जब 30 मीटर का एक सेल हम सपोज कर लेते हैं सर है, तो सर उसमें जो एलिवेशन है वो उस 30 मीटर का एक एवरेज एलिवेशन होगा सर?
Average elevation होता है. One cell is not 30 meter, its resolution is 30 meter. And one cell may consist of some pixel. One pixel total is 30 meter. In that there may be more than one cells also. Yes, but for hydrological purposes, for stream delineation and all, this is more than sufficient. This accuracy is found to be more than sufficient. In fact, मैनुअली जो करते हैं उसमें तो एक डॉट में कई मीटर चला जाता है. Okay. Right. Now we do what is known as styling. Styling is another thing which is associated with all GIS system. See, we are working in 3D environment, but obviously we can see in 2D. So to get 3D effect in 2D picture, you do its coloring and color rendition in such a way that in 2D you get the 3D picture. That's what you see in Google Map and all. They are all 2D things containing 3D features, but you get a 3D feeling. That is known as styling. Even in Google Map and all, what is done is styling. So styling for different purposes, it is all trial and error. People with their experience, different sort of styling standard patterns are there, they have used and all. And finally, there are many methods of styling. You may have your own method and you use whatever is suiting to you. So here, let us say DM field, we will do some styling for better visual appearance, and this is how it will look. Now, same picture, which was in black and white, it is given some colors. And what is the difference? Here you see, if you go style, it says the darkest one, that is this like black, is highest elevation 350. Then brown one 283. Then light brown 216. Then yellow is next lower. Then green is next lower, and blue. So now you can get an idea. This is the highest area. So from here flow is generated, then it comes to light brown, then it goes to yellow, from yellow it goes to green. Similarly, this area, if you see, from brown it is coming to yellow, from yellow it goes to green, and if you blow it further, you can see wherever blue is there, those will be streams. So now seeing this, previously in black and white, it was some negative sort of thing. Now you are finding this is one area where flow is generated. This is one area where flow is generated. Here also we can see which area flow is generated. So you get a 3D feeling. That's the only advantage of doing this styling. Otherwise, processing and all, it does not help. So this is styling of DM field. The field DM has been styled. Now after that, next step 3F is, please note down these steps. You may need it later on. 3F is generate the flow when we do actual hands-on practice. Now you generate the flow directions. As I told you, it does like this. It makes various cells, and from one cell to another like that, what is the flow directions it generates. And then when flow from two places meet, it makes a stream, how streams are generated. So you derive the streams also. And here a term which is used is known as stroller order. This is the term, as if you remember, I told you in manual thing, Stream, you will take ridge of your contour map and all. Now, which is real big stream, which is only a trickle, is not possible. For this, there are various schemes. One of the most popular is stroller order. There are other orders also. Stroller order, what the concept is, when you generate the stream, let us say there are two streams and you give them stroller order 1. 1 is smallest. Now when two streams of the same stroller order they meet, it makes the next stroller order. It will become a stream of 2. So it means 2 is bigger than 1. But if another stream of 1 is meeting in 2, it will still remain 2. There will be no change. But let us say there is another stream of 2 meeting with 2, then next will become 3. This is how this stroller order is. Two streams of same stroller order, when they meet, they generate next stroller order stream. So now if you quantify the streams, you will know 1 is smallest, 2 is biggest, 3 is further bigger, 4 bigger, like that. And in your area, you can find out what is the highest stroller order, maybe 9. And then you can also find out for your purpose, what will be the significant stream, maybe 5 to 9 you will like to take, or maybe 4 to 9 or 6 to 9, like that. We'll see this as we go along. And then you will work only on 6 to 9. Otherwise, there will be in numerous streams on the surface. I will show you. It becomes very difficult to work on them. So this quantification of flow is stroller order. So we also developed the stroller order in this our DMs. And then this stroller order file, you save it. This is a data file. This is raster file. You style it and save it, and I will show you how it looks like. Now, this is a stroller order file. Now I will just, zoom out. Now you can see this blue color, all are streams, and there are hundreds and thousands of streams in this. Really speaking, manually तो आप 2-4 ही mark कर पाते. The darker one may have more flow, the smaller one may have less flow. Now, if you start working in all these streams, it will become impossible to work. So what you do is you try to find out threshold stroller order for your particular case, and then you work on that only. So then you identify the significant stream based on stroller order. How it is done, I will show you in next slide. Like in this case, stroller order 5, I found it to be most significant. How, I will tell you. Now, see this. Now, when I have given, I started from stroller order 3, still there were a lot of streams. Then I started with 4, there were a lot of streams. Then 5, this is with 5. Now see, you can, number 1, of course, this is again zoomed in picture. Number 1, you can see clear streams. Second thing, this background light blue, what you are seeing is OSM map, which was showing this river, and this dark blue are river streams generated because of your GIS. And you see it is more or less telling. You can see here, it is more or less telling. When you try with 6, probably it is not as good as 5. So like that, you have to start maybe from 3, 4, 5, 6, 7. And it's not hard and fast. Maybe somebody may work with 6 also, does not make much of difference. But where you feel you are getting best representation of this, that stroller order is the useful stroller order for you. Sorry. Here. So I have taken stroller order 5 as the threshold level, and this value is used for further processing. Using this threshold stroller order, which were derived at 5 in this case, you will now delineate the channel networks and drainage basins. How many channels are there in the DM? We have taken a bigger DM. Our relevant portion may be a part of that. We will further, trim it later on. So for this also there are processing tools, and you create some file. First you create what is known as flow direction file. We have saved it as flow dr. It is again a dat file, means raster file, and do the styling. Now this is how it looks like. Here also you can see what is meant by what. Blue is flat, then higher, 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 higher. So basically here, if you sort of, this is not used for processing, but this you can get an idea how flow is generated. These are your streams, then which are the bigger points, from which direction flow is coming, from which direction going, that sort of idea. You can, again, a visual representation, nothing more than that. In fact, this file is only for getting a visual idea that from which direction water is coming and finally which stream it is joining. See here, there is one stream, there is another stream. So this is one. Second, which is really useful and we use it also for further processing, is you create the channels. We create the channels and save them, style and save it. The channels using the threshold Stoller value. Now, if you see, this is how the channels they look like. And if you here, the thinner one is smaller channel, it mixes into this, it becomes a bigger channel. Like that, there are so many channel networks. You can see this is one network starting from here, going up to here. There is another network here. So you have created channel. Now this includes all the channels in this, not only relevant to you, all channels. If you do further zooming in, you can see channels. Now your area may be somewhere here only, or maybe this one may be your area. We don't know. We will do this streaming, but whatever those two mosaic GM or combined, DMs we have taken for that full area, all channel network. Now you can see how this is what I was telling, the visual appearance also. Now you can see some thin channel here, then it joins, makes another, or see here, one channel, it joins another, they make like this side some channel, this side some channel, and finally somewhere here they are going. Similarly, this is one network. Like that, there are many. So at this stage, it has earmarked all the channels. So this file will contain all the channels, including outside the relevant catchment area also. Trimming how it is done, we will do afterwards. Similarly, you created channels, you also create drainage basins and save the file after styling. So this will look like this here. Now there is one drainage basin here, one is here, one small is here, one is here, one, and number of, maybe yours may be this small one, or maybe a part of this, or maybe something else that will do, but all drainage basins corresponding to those channels which we have seen have been earmarked. See, now the advantage is how fast things can be done and how accurately. Doing it manually would have been hell of a job. So we have done this. So this file also will show all catchment area and drainage basin, including the portion which is not contributing the flow at point of our interest. It contains for the whole that DM. So now for finding out our relevant catchment area, first thing, if you remember, I have told you in the same stream, your catchment area or drainage basin will depend on your point where your bridge is there or your point of gauging is there, and we call it outflow point here. This is the terminology used by Europeans. TU Delft uses same. So for this, we have to give the point, our point, and with respect to that, it will earmark or it will delineate the my relevant catchment area. So for that, what you do is, first you use the coordinates, the UTM easting and northing coordinates, which we have seen that day, and take your cursor to near that coordinates, then zoom the map to the maximum extent I will show you, and then you pick up the coordinate of this. There is a coordinate capture tool. There is a coordinate capture tool in this. So, and please remember, whatever UTM easting northing you have taken and what coordinates you note down here, there will be some minor variations. Does not matter. I will tell you why it isn't so. And here you will capture the coordinate, exact coordinate of your bridge. Like in this case, this is XY. If you remember last time, our UTM easting was 3, 4, 5, 4, 3, 2. It has become 6, 7 here. Similarly, northing coordinate was 2, 7, 9, 7, 8, 8, 4. It has become 8, 8, 6. Does not matter. Don't worry. And I will tell you reason here. You can see here. Now here. These are the coordinates. Using this, you go to nearest place, and then coordinate capture tool is there. Let me make it bigger. Red dot, what you are doing is coordinate capture tool. Now this is your bridge, this is your railway line, you can see this is your stream and this is your point coordinate. In this it is not clear, but many times what happens is you see two type of streams in this coordinate capture screen. One is this dark color, this streams, that is basically the stream made by your QGIS. Another is sometime in background you see light blue color, that is OSM map. Always capture your coordinate on the dark color scheme, because what happens is any curved line, let us say some line is curved like this, your computer, how does it plots the curved line? It plots as a series of straight line like this. So this point in your QGIS will come here. After processing, it will go nearer to that. But if you take point here and then try to process, your QGIS will give error because it does not recognize this point. It recognizes this point. But this, approximation is so small that ultimately it does not make much of the difference. Therefore, always take the point on this dark blue line, and here it will capture its latitude, longitude, and your XY or easting and northing coordinates. So using this coordinate, now for this point, we will use further commands in QGIS and we will delineate our catchment area. So once you have done this, then there is another command for deriving the catchment, or what is known as upslope area. Term used is upslope area here. So these captured coordinates are used. As I told you, you will see in the end, if I get time around 1.5 hours or something, then actual exercise I will do it on QGIS and show you. Otherwise, maybe hopefully when you come here for the concluding part of phase 2, maybe the time, if it depends on whether we get the time. So using that upslope area delineation command, you will get your catchment, and that file we have named catchment file, and this is raster file, data file. SDAT is a extension which is. Now, as I said, raster file are not as good in viewing. You like vector files, they give you a better idea. Raster file will be cell with rectangular boundaries and all. So there are tools where you can convert raster file to vector file. So you convert this raster file to vector file and give it name catch polygonal file. Vector files are also known as polygonal file. So we convert this catchment to, let us say, another name, we give it catch poly, which is a shape file, SHP shape file, which is vector, and style it. Again, as I told you, for different purpose, different styling is there, and then you see how it looks like this one. Out of all these streams and everything, this is your catchment area, like this. We'll further blow it and see. Your streams starts from here like this, and this is your outflow point. Flow is like this. So somewhere here is your catchment area. Now, as I told you, this is only this. So what we will do, we will remove all this unwanted things from here, and we will concentrate only this. So this is next step. We will purge our this thing. So next is clip the channels and DM layer. So clip the channels to only see the streams which are inside the catchment area. Now we will see only those streams which are inside the catchment area, and we have named it as channels clipped. Let us, here you can see, and I have zoomed it out. Now this red one boundary is your catchment area boundary, and these are various channels. This you can see your railway line also, and this is the point here, your bridge is there. Again, visually now you are confirming that yes, you are on the right track. You are, and you can see various villages, other features. And on this, if somebody says what is the longest stream, this will be probably longest stream. Here like this. This will be the longest stream. So now catchment area and my channels, I have trimmed everything else. I have only taken what is relevant to me. This DM also, previously my whole DM was there. Now DM also I will trim. Similar way, I will clip the DM also, and I will keep only my. So this is my relevant DM. Previously DM was further rectangular, very big. This is the DM for me, which is clipped DM, which I will be using for further processing. Right? Up to here it is okay. Now we have derived required catchment, required streams, required DM. Starting from a bigger part, we have come to the part which is relevant to us. Clear?
Yes, sir.
Okay. Anybody have any doubt? Please ask it. So this is the third step, which is a major step about processing the DM. Now we have processed it, brought it to our level, the micro level, and then now we will start various measurements or assessments from this. So first thing, in the properties, if you remember, once you know the DM, this is equivalent to marking on your topo sheets, all those river streams and all, let us say, equivalent to that. Now we have to find the catchment area. Very, very simple. There is a command in QGIS using the save file catch poly. There is a direct command which is known as field calculator. Using that, you can just say catch poly, use field calculator, and you can get the area. I will show you how it looks like. Like this it will look, and here area is coming, and we have set meter as the command as default, our unit. So this is in square meter, 162,080,418.24. You don't have to do anything. So fast and so accurate. And this many meters I am noting down. You may also note down because these values will be using up to end. So now my value of A has come to 162.08 square kilometer. So what type of catchment it is? Is it small, medium, or large?
Medium.
Medium. So this is a medium size catchment area. So now we will use this example for working out Q50 for a medium size catchment area. Same example, and same we will use for bridge planning for deciding what you call span arrangements and depth of founding and all. Area ho gaya. Now centroid, because we need to mark the centroid. Very simple. Again, use the catch poly layer. There is a command for centroid of any shape, of any irregular geometry shape. Just use it, and you can see here this dot is the centroid within no time. So centroid is also marked. Next is L, longest stream. So for longest stream, what you do is you blow it up, you zoom it to a largest scale and start from the opposite end. I will show you, and here, and mark the longest stream like this. You start from here, this tail, and then you can select. Actually, the stream is in various segments when you mark. So every segment you keep on selecting. So you start selecting from here and you select up to here. Then you merge those segments, and that becomes your longest stream. So now you removed all other streams also because you're interested in this stream only, not anything else. So you have marked only the longest stream. And once you have marked the longest stream, then again there is a geometry tool in field calculator to get its length. Within no time you get that, and I have given that length as name L length. So the length is 23,256.61 meters. So you have marked the length, which comes out to, in this case, if you round it off, 23.257 kilometer. Okay, area ho gaya, length ho gaya, no problem.
No sir.
Right. अब हमें सेंट्रोइड का नियरेस्ट पॉइंट निकालना है स्ट्रीम पे फर्स्ट, एंड फ्रॉम दैट पॉइंट टू माय ब्रिज वो लेंथ निकालनी है, दैट इज एलसी लेंथ. तो उसके लिए ऑन द लॉन्गेस्ट स्ट्रीम locate the point which is nearest to the centroid of catchment area like this. So this is my stream, L stream. I have got centroid point also. So why do I use a command of straight line, and then I rotate here there the straight line in such a way that its length is minimum, so that will be the nearest point. So by that I have located the nearest point, the intersection of this straight line and all. So this is the point which is nearest to my centroid. Then from this point to my bridge. So what I will do, there is another command splitting any feature in two. So whatever was my longest stream, I will split into two parts. This part and this part. I will remove this part and keep this part. That will be my LC stream. So next is mark the stream from this point to bridge location. See here. I have split and removed this. Now this stream is my LC stream. And once I know the stream, very easy. You can get its length within no time. Like L stream, LC stream, there are different streams. So you measure the length of this LC stream by using same field calculator, and you can see I have given it its name as LC length, and this is coming in meters this much, 10673.62, and then you can round it off to kilometers. So my LC value is 10.674 kilometer. Now what is the only thing left out? I have got A, I have got centroid, I have got LC. What is the last thing which we need in catchment area? Slope. So for slope, basically you will need length elevation profile. Once you know length elevation profile, then you can divide into segments, and from those segments you can work out the slope. So next is collecting the data for calculating S. So for that, again, using your field DM and your L stream profile, you make them interact with each other, and you plot a length elevation profile which looks like this. So this is your bridge, this is your farthest point, and length is given as X coordinate. As you move your cursor here, like you will take this as one, this is another one, this another, this one, this one, this one, this one, this one, like that. Divide into 10-15 segments, and for every segment your X and height you get. The moment you put your cursor there, you will get your X distance. Here of course only thing is X will be from here, measuring from this at 0 point, and height will be, it will get the reduced level. If you want your distance from here, then your length of longest stream minus X. If you do, you will get distance from here. That's very simple. So from this length elevation profile, you have noted down this. These are various segments, like I have divided into 11. This is will be equal to L only, and then last segment this will be 0, and these are the, they are increasing. So the bridge is at RL 126 and the farthest point is at RL 189. Now once you have got this length elevation profile data, I will tell you there is a formula, there is a table, put it in. For that I have made an Excel sheet, you will see there. You can put it there and calculate S also. So the catchment properties we are able to assess using this GIS system in this way. Okay.
Sir.
Any doubt or any question about